So I've been working on something lately that I think is going to really help out as far as the Coriolis effect goes, specifically horizontal Coriolis. I hadn't worked out a new way of doing vertical Coriolis, but when it comes to horizontal Coriolis, the formula that I use most of the time to calculate it uses the omega constant multiplied by the range to the target in feet, multiplied by the time of flight in seconds, and then multiplied that by the sign of the latitude that you're on. And it actually works out pretty good. Your result is usually it's going to be the however many feet the deflection is, which, if you know anything about Coriolis effect, it's not really a matter of how many feet, it's a matter of how many inches. Even if you're at like 2,000 yards, I mean, we're still only talking like maybe 6 inches of deflection. But it is a deflection nonetheless, and I don't know, I could use a normal ballistic calculator that would just solve that for me, but to me, it's kind of fun being able to actually do it yourself out in the field, but the new way that I've kind of worked up is actually using figuring out what the rotational speed of the Earth is at a given latitude. And actually, I built a whole chart, and I've got the rotational, and it's kind of a painstaking process, but I figured out the rotational speed of the Earth at each latitude as far as North America goes. So with the southernmost latitude being 24 degrees north, and the northernmost latitude being 49 degrees north. And I figured out what the rotational speed is at each one of those latitudes, and I converted it to feet per second, because the reason why this is going to work out is because if you figure out what the rotational speed is in feet per second, you can multiply that by how many seconds. You can multiply the difference of, say, if you're shooting at 34 degree latitude and you're shooting towards the 35 degree latitude, you can take the difference in the rotational speed between those two latitudes, which would be, I don't know, somewhere around 20 feet per second. And then you can take that and you can multiply that 20 feet per second times the amount of flight time it takes to go from 34 degrees to 35 degrees. So theoretically, if you could shoot around that far, but we're talking like hundreds of miles to do that, maybe even more than that. I don't know exactly, but the point is, that just kind of illustrates the point there, is you would use that difference in rotational velocity and then multiply that by however many seconds of flight time the bullet takes to get there, and that would give you your deflection in feet. And it's actually pretty cool. I actually come up with this idea in a dream the other night, which sounds crazy, but I work a lot of problems out in my sleep sometimes. I don't know if that's a good thing or not, but so like I was working out a way to calculate so for instance, where I like to shoot at, my firing position, the latitude there is 34.73, like 596 degrees north, and then where the target is 34.74161 degrees north. And so the difference in rotational velocity between that specific latitude and the specific latitude where the target is I think the difference in rotational velocity is like 0.171. I can't remember exactly, but it's like 0.17, so like almost 0.2 feet per second difference in rotational velocity. So if the bullet, and we're talking about a distance that's like 1,900 yards here, so if the bullet takes 3.18 seconds to get there to that distance. So you would take that 0.17 feet per second difference, and you would multiply it by 3.18, and then you would get your actual deflection. Now, that would give you the actual deflection if you were shooting perfectly north and south. Now, if you're shooting kind of like northwest or something, or if or vice versa, if you're shooting southwest or southeast, doesn't really matter. You would actually have to figure out what your azimuth is, and you can do that easily with like using a compass rose, and then you would use basically an angle cosine or a percentage of angle, so if you're not exactly shooting north, you'd figure out, well, I'm shooting, say, 70% north, 70% of the way there, 70% of the angle, as it were, and you would multiply that deflection by 0.7, and it would give you your actual deflection at the angle you're shooting at. So I'm setting this up in a way that it can be, the math can be real simple and doesn't actually require if you're out in the field, it won't actually require a calculator that uses trig functions, and you can do it with simple addition and multiplication and come up with a good, correct firing solution. It may be a lot to take in, and I'm probably going to have to do a video illustrating how this actually works, but I actually compared it to using the old formula, and it's almost exactly the same. The deflection I come up with is pretty close. It's within 1 inch at 2,000 yards, So, I mean, I don't know about you, but I'm not good enough of a shooter to, perfectly move a bullet 1 inch, from one round to the next at that range. Maybe at 100 or 200 yards, yeah, that's not really a problem, but 2,000 yards or even 1,000 yards, I don't think you could do it. I mean, maybe like the top of the top best F-class shooter might could do it, but not me personally. So being off by 1 inch of Coriolis deflection is not going to matter that much, because your group size at that range, even if it's a 1 MOA gun and it's shooting perfectly at 1,000 yards, that's 21 inches of deflection of group size. So 1 inch is going to get lost in that 21 inch group size pretty easily. That's what I'm saying. And even at 1,000 yards, your group size is what, 10.5 inches is 1 MOA, which everybody knows. You throw in the wind and all that stuff in between there, between you and a 1,000-yard target, and it's going to be, your group size is not going to be 1 inch. If you've got a 1 inch gun at 100 yards, at 1,000, it's probably going to be more like 15 to 18, maybe even 20 inches. It's going to be pretty big, so that's why, these guys that are shooting and they're wanting these tiny little 0.1, 0.2 inch groups at 100 yards is because at 1,000 yards or further, those groups open up pretty big, and they can be 5 inches or 6 inches out there pretty easily. They can go from a quarter minute to 1 minute of angle real quick when you add in all the environmental factors like wind, and then if you're shooting up or downhill, shooting through different barometric pressure zones, that's going to affect the way it shoots. Everything, so, but I just think it'd be pretty cool to come up with a way to actually calculate your Coriolis without having to have a trig function on a calculator. You could just do it by hand. It will require some pre-planning. You will have to have some prior knowledge of what the rotational speed of the Earth is at specific latitudes and that sort of thing. But once you build that chart up, you'll never need to have to use a calculator to make another chart. Just don't lose your chart, and don't Don't let it get destroyed in some way, shape, or form. So, anyways, I'm going to leave you guys with that. You guys let me know what you think down below in the comments.